Hi, this is Chris. In this video, I'll start by looking back at the state machine to compute the reciprocal of the divisor as a springboard to where I'm planning to take the discussion on floating point division. The way forward will start by revisiting floating point multiplication. The path will eventually lead to using other algorithms to compute the reciprocal of the divisor. However, before doing that, I want to make note of something that happened since I posted my last video. At the time of this recording, this channel now has 116 subscribers. My opinion is that digital logic is a niche topic on YouTube. Designing circuits to perform floating point arithmetic is a niche within the topic of digital design. That is, I have always viewed this channel as covering a niche within a niche. Furthermore, when I told friends and family about my YouTube channel, I said I would consider myself wildly successful if I ever reached 100 subscribers. With your help, I have become wildly successful. Thanks for subscribing. Thanks for your feedback on the videos, and thanks for sharing the channel with others. On to 200 subscribers. Before beginning on a new algorithm for computing the quotient, I need to point out some problems with computing the reciprocal as presented in the previous video. The first problem with the code in the previous video is that the code assumes that both subtraction and multiplication can complete in a single cycle. I'd buy that subtraction can complete in a single cycle. However, for multiplication to be able to complete in a single cycle requires slowing the system clock down a lot and sacrifices performance. One of my goals is to make the floating point operations as fast as possible. So, in that regard, the code presented in the last video is, shall we say, overly optimistic? The second problem is generic to any solution which computes the reciprocal as a separate step from multiplying the reciprocal by the dividend to compute the quotient. If the divisor is a subnormal number, the reciprocal may be computed to be infinity. Consider the following case. 1 times 2 to the negative 2 power divided by 1 times 2 to the negative 16th power. If we multiply by the reciprocal of the divisor, this becomes 1 times 2 to the negative 2 power times 1 times 2 to the 16th power. The product then is 1 times 2 to the 14th power. This number can be correctly represented as a normal binary 16 number. Note that the reciprocal of the divisor is 1 times 2 to the 16th power. This is a problem. The reciprocal can't be represented as a normal binary 16 number. We would normally have to round this number to positive infinity. When we multiply the dividend by the reciprocal, the product would also be positive infinity. As you can see, when I calculate the result by hand, the quotient, that is, the dividend multiplied by the reciprocal of the divisor, is a finite number which can be correctly represented by a normal binary 16 value. Having computed the quotient by computing the reciprocal of the divisor as a separate instruction from multiplying the dividend by the reciprocal, I'm now going to change strategies. I'm going to build a circuit which calculates the reciprocal and multiplies by the dividend in a single instruction to avoid the problem of artificially creating an infinite quotient when it's not necessary. This decision is arbitrary. Depending on your circumstances, computing the reciprocal in one instruction and performing the multiplication in a separate instruction may be the better choice. In future videos, I will discuss cases where the computation of the reciprocal as a separate instruction is the better choice, but not today. I now want to move on to a different method of computing the reciprocal. Doing this is going to take multiple videos, and I want to start by revisiting how the product of two significands is computed. As you may recall from my series on implementing a circuit to multiply two floating point numbers, I use 4 different methods for computing the product of the significand. Use the Verilog multiplication operator, and let the Verilog compiler work out the details for itself. Implement a generic sequential algorithm which adds the partial products. compute the partial products, and as much as possible, add the partial products in parallel. Compute the partial products using 3-2 compression, that is, a Wallace tree, to reduce the time penalty of propagating the carry information. In this video, I'm going to introduce a different strategy for multiplying the significands, Booth's method. To understand Booth's method, I need to first cover a special feature of binary numbers. I've been using this feature, but it's really been in the background. I want to re-examine my C++ code to implement the binary 16 data type. This code was introduced in the video Building an FPU in Verilog Floating Point Division Part 3. In the header file hp.hpp, I define several masks. I want to focus on exp mask. In line 269 of hp.hpp, I use exp mask to extract the biased exponent of the binary 16 value. I defined exp mask so that the 5 least significant bits of the mask are set to 1. To extract the biased exponent value, the code first shifts the exponent field right to move it into the 5 least significant bits, and then the code uses the mask value to clear any bits outside of the exponent field. Let's examine the expression used to compute exp mask in more detail. The expression 1 shifted left by hp nexp is equivalent to 2 to the hp nexp power. Since hp nexp is defined to be 5, this first expression is equivalent to 2 to the 5th power. Now let's look at the next part of the expression, subtracting 1. 1 is equivalent to 2 to the 0th power. So the expression used to create the mask can be looked at as 2 to the 5th power minus 2 to the 0th power. This expression, which is a difference of powers of 2, yields a string of contiguous bits set to 1 such that the string is 5 bits long and the least significant bit of the string is bit 0 of the integer mask being created. The logic to extract the biased exponent could have been done differently if I had used a different definition for the mask. If the mask had been 5 ones followed by 10 zeros, that is the hexadecimal value 7C0, then I could use the statement fexp is equal to the quantity datum ended with exp mask shifted right by hpn sig to extract the exponent. This value of the mask is equal to 2 to the 14th power, plus 2 to the 13th power, plus 2 to the 12th power, plus 2 to the 11th power, plus 2 to the 10th power. I assert that this expression is equal to 2 to the 15th power minus 2 to the 10th power. Let's see if I can prove that. 2 to the 15th power is equal to 2 to the 14th plus 1 power. And this is equal to 2 to the 14th power times 2 to the 1st power. And that's equal to 2 to the 14th power times 2. And that's equal to 2 to the 14th power times the quantity 1 plus 1. And using the distributive property of multiplication, this is equal to 2 to the 14th power plus 2 to the 14th power. Similarly, I can show that 2 to the 14th power is equal to 2 to the 13th power plus 2 to the 13th power. 2 to the 13th power is equal to 2 to the 12th power plus 2 to the 12th power. 2 to the 12th power is equal to 2 to the 11th power plus 2 to the 11th power. And 2 to the 11th power is equal to 2 to the 10th power plus 2 to the 10th power. Using this information, it follows that 2 to the 15th power is equal to 2 to the 14th power plus 2 to the 13th power plus 2 to the 12th power plus 2 to the 11th power plus 2 to the 10th power plus 2 to the 10th power. Subtracting 2 to the 10th power from both sides, we get 2 to the 15th power minus 2 to the 10th power is equal to 2 to the 11th power plus 2 to the 13th power plus 2 to the 12th power plus 2 to the 11th power plus 2 to the 10th power. Quod erat demonstratum. So, To get a string of 5 consecutive 1 bits with its least significant bit in bit 10, we can use the expression 2 to the 15th power minus 2 to the 10th power, that is 2 to the 10 plus 5 power minus 2 to the 10th power. You should be able to see that in the general case, we can use the difference of 2 powers of 2 to get any arbitrary string of n consecutive 1 bits with the string's least significant 1 bit in bit m using the expression 2 to the n plus m power minus 2 to the m power. Booth's method for multiplication is built on this idea that we can collapse strings of consecutive 1 bits into the difference of 2 powers of 2. In previous videos, I used the hexadecimal value 4248 as the binary 16 value which approximates pi. Extracting the significand field and adding the implied leading 1 bit, we have a significand value of hexadecimal 648. I can write this in binary as 11001001001000. I have a string of a single consecutive 1 bit with its least significant bit in bit position 3. Expressing this bit string as a difference of powers of 2, we get 2 to the 4th power minus 2 to the 3rd power. A string of a single consecutive 1 bit with its least significant bit in bit position 6. Expressing this bit string as a difference of powers of 2, we get 2 to the 7th power minus 2 to the 6th power. And a string of 2 consecutive 1 bits with its least significant bit in bit position 9. Expressing this bit string as a difference of powers of 2, we get 2 to the 11th power minus 2 to the 9th power. So, the significand of the multiplier, described as differences of powers of 2, is 2 to the 11th power, minus 2 to the 9th power, plus 2 to the 7th power, minus 2 to the 6th power, plus 2 to the 4th power, minus 2 to the 3rd power. In an earlier video, I performed the calculation of the area of a circle with the radius of 20 centimeters. This, of course, is done by squaring the radius and multiplying by pi. The radius squared is 400. Written as a binary 16 value, this is the hexadecimal value 5E40. This has a significand of hexadecimal 640. To compute the product of the significands of 400 times pi, we need to compute the product of hexadecimal 640 times the quantity 2 to the 11th power minus 2 to the 9th power plus 2 to the 7th power minus 2 to the 6th power, plus 2 to the 4th power, minus 2 to the 3rd power. To help us decode the multiplier, as differences of powers of 2, we're going to prepend a leading 0 and append a trailing 0 to the significand of the multiplier. Our significand then becomes 011, 001, 001, 0000. These extra bits are needed because we're going to examine the multiplier 2 bits at a time in order to detect the beginning and ending of strings of 1 bits. We're multiplying two 11-bit quantities, so we know the result can be contained in 22 bits. We create a 23-bit register and initialize it to contain all zeros. For now, I'm postponing the explanation of why the extra bit is needed. To start, we examine the 2 least significant bits of our modified multiplier value 0110010010000. The 2 least significant bits are 0, so we make no changes to the 23-bit product register. To prepare for the next iteration, we shift both the product register and the modified multiplier value right by 1 bit. The modified multiplier value becomes 0110010010000. This represents the current state of the multiplier register. Boxes with digits represent bits in the multiplier which haven't yet been processed. After shifting the product register right, this represents the current state of the product register. Blank boxes represent bits which are 0, but haven't yet been computed by Booth's method. You should be able to see that for the second and third iterations of Booth's method, the last 2 bits of the multiplier register will be 0. So like the first iteration, we only perform a right shift on both the multiplier register and the product register. After iterations 2 and 3, the new multiplier value is 011, 001, 0010. Now, the 2 least significant bits of the multiplier are 10. This means we have detected the beginning of a string of 1 bits. We subtract the multiplicand from the 12 most significant bits of the result register. This subtraction corresponds to the partial product formed by multiplying hexadecimal 640 by the term -2 to the third power. You should now be able to see why I created a product register with 1 extra bit. We just subtracted from 0, so we need a sign bit to hold the correct result. Again, to prepare for the next iteration of Booth's method, we shift both the product register and the multiplier value right by 1 bit. Note that because the product register holds a negative value, we must perform an arithmetic right shift. That is, we don't shift a 0 into the most significant bit of the product register. We propagate the sign bit, which in this case is 1. This was also true for the previous iterations when the sign bit of the product register was 0. Now, the 2 least significant bits of the multiplier are 0, 1. This means we've reached the end of our string of consecutive 1 bits. In this case, we add the multiplicand to the 12 most significant bits of the product register. This causes the value in the product register to once again be a positive value. This addition corresponds to the partial product of the multiplicand hexadecimal 640 multiplied by 2 to the 4th power. I've shown what happens when the last 2 bits of the multiplier register are 00, 01, and 10, so the details of processing iterations 6 through 10 can be skipped. For the 11th iteration, the 2 least significant bits of the multiplier register are 11. Now what do we do? Nothing. We treat this the same way as if the 2 least significant bits of the multiplier were 00. We're in the middle of a string of 1s. We only add or subtract the multiplicand from the product register at the beginning or end of a string of 1s. One more time we prepare for the next iteration by shifting the multiplier register and the product register right 1 bit. For the final iteration, the 2 least significant bits of the multiplier register will be 0, 1. So add the multiplicand to the 12 most significant bits of the product register. Finally, when we finish the 12th iteration of Booth's method, the product register contains hexadecimal 274200. Since this is the product of 2 unsigned integers, we can strip off the sign bit to get our 22-bit result. Let's summarize. During each iteration, if the last 2 bits of the multiplier are 00, we neither add nor subtract to or from the product register. 10, we subtract the multiplicand from the 12 most significant bits of the product register. 01, we add the multiplicand to the 12 most significant bits of the product register. 11, we neither add nor subtract to or from the product register. To prepare for the next iteration, we perform a 1-bit arithmetic right shift of the product register, and we shift the modified multiplier value right by 1 bit. The generic sequential significand multiplication circuit presented in an earlier video generated 11 partial products and required 10 additions. Now, As I've explained Booth's method, it is a sequential algorithm, and instead of summing 11 partial products, we had to sum 12 partial products. This means that as I've described it here, Booth's method is less efficient than the previous methods which I've described for multiplying two significands. However, I'm not done yet. There is also a modified version of Booth's method. As before, we pad the multiplier with leading and trailing 0 bits. We also need a product register which is 24 bits wide. In the modified version of Booth's method, we examine the last 3 bits of the modified multiplier value. When the last 3 bits of the multiplier are 0, 0, 0 or 1, 1, 1, neither add nor subtract to or from the product register. 0, 0, 1 or 0, 1, 0. We add the multiplicand to the 13 most significant bits of the product register. 0, 1, 1. We add 2 times the multiplicand to the 13 most significant bits of the product register. 1, 0, 0. We subtract 2 times the multiplicand from the 13 most significant bits of the product register. 1, 0, 1 or 1, 1, 0. We subtract the multiplicand from the 13 most significant bits of the product register. Then, in preparation for the next iteration, we perform a 2-bit arithmetic right shift on the product register, and we shift the modified multiplier value right by 2 bits. As you can see, because each iteration of the modified Booth method consumes 2 bits of the multiplier, we only need to perform half as many iterations. In other words, we've reduced the number of partial products which need to be summed from 12 to 6. Now we're getting somewhere. Still, we have the problem that, so far, as I've described Booth's method, it's a sequential process. It's time to parallelize the algorithm. Once again, I'm going to apply 3-2 compression, that is, a Wallace tree, to avoid as much as possible the cost of propagating the carry bit. Let's review how I previously used 3-2 compression. Remember that for 3-2 compression, we take 3 of the partial products and compute 2 outputs. This output represents the sum portion of the output of 3-2 compression. Remember that since the 0th bit from the first partial product doesn't line up with any bits for the other 2 partial products, we can simply copy the 0th bit into the sum. These missing bits from the other 2 partial products are effectively 0. In a similar manner, since there is no Z1 bit to compute the sum from the column which has X1 and Y1, we only need a half adder. For bits 2 through 10 of the sum, there are corresponding bits in the partial products X, Y, and Z. For these bits, we need a full adder. At this point, we have consumed all of the bits in partial product X. We have bits Y11 and Z11, and we treat X11 as 0, so we only need a half adder to compute the value of bit S11. This mirrors the computation of bit S1, where we have only bits X1 and Y1, and we could treat bit Z1 as 0. Finally, we simply copy bit Z12 into bit S12. Again, this mirrors how we computed bit S0. This output represents the carry portion of the output of 3-2 compression. Bits C2 through C12 were generated by the same half adders and full adders which we used to compute bits S1 through S11. There is no need to compute carry bits C1 and C13 because there won't be any carry out generated by bits X0 or Z12 respectively. When applying 3-2 compression to the modified Booth method, there are changes from the earlier multiplier using 3-2 compression. The first is that the partial products are 2 bits wider. You can probably already see where the 2 extra bits come from. Each partial product is one of 5 possible values. 0, the multiplicand, 2 times the multiplicand, the negative of the multiplicand, and 2 times the negative of the multiplicand. Storing the multiplicand only requires 11 bits. Storing 2 times the multiplicand requires 1 additional bit. Storing the negative partial products requires an additional bit for the sign. The second change from my earlier use of 3-2 compression is that the partial products y and z are shifted left 2 and 4 bits relative to the partial product x. This, of course, is a consequence of processing 2 bits from the multiplier to generate each of the partial products. Because bits y0, y1, z0, and z1 are implied to be 0, we can simply copy bits x0 and x1 into bits s0 and s1 respectively. We can compute bit s2 from bits x2 and y2 using a half adder. Similarly, we compute bit s3 from bits x3 and y3. We compute bits S4 through S12 from their corresponding X, Y, and Z bits using a full adder. It's time to compute bits S13 through S16, but now things are different. We can't simply treat the missing bits in the partial products X and Y as 0. That is, we can't simply use half adders to generate bits S13 and S14, nor can we simply copy bits S15 and Z15 into bits S15 and S16, respectively. The partial product bits X12 and Y14 aren't simple digit bits, they're sign bits. In this table I've replaced X12 and Y14 with S sub X and S sub Y respectively to indicate this. In this version of the table, I've sign extended the partial products x and y. To compute the sum bits S13 through S16, we need to use full adders on the sign extended versions of the partial products x and y in conjunction with the partial product z. Now that I've covered how to compute the sum bits using 3-2 compression, it should be obvious how we compute carry bits C3 through C17, since these bits are generated by the same adders which are used to generate sum bits S2 through S16. As before, there will be no carry bits C1 and C2 generated by partial product bits X0 and X1 respectively. For each successive stage of 3-2 compression, we will need to sign extend the partial products, but we can save resources by only sign extending as needed. That is, it isn't necessary to sign extend all of the partial products out to bit 23 at the start. For comparison, here is the schematic generated by Vivado for the original 11-bit by 11-bit multiplier from the earlier video, side by side with the schematic for the new multiplier, which leverages the modified Booth's method. When I made the earlier videos for the significand multiply circuits, I knew about Booth's method. Because of this, it's reasonable to ask why I didn't present this method earlier. This video series is in some ways a video blog. Learning how to design floating point hardware is an ongoing project for me. Much of the information presented in the videos is information I have only recently acquired or developed. I didn't attempt to present a Booth's method multiplier because I knew that I would have to address the issue of the partial products being signed quantities, and I wasn't sure how to fit that into the 3-2 compression scheme. This means I wasn't sure how to parallelize a Booth's method multiplier. It wasn't clear to me whether I would need to extend all of the partial products to the left out to bit 23, counting from 0, or if I could simply sign extend as the additional bits were needed. I hadn't worked out that problem yet, so I wasn't prepared for what might go wrong. I only addressed the problem because I was backed into a corner. The design, which I'm going to present in upcoming videos, uses Booth's method, so I finally had to work through the issues associated with the signed partial products. It's time now to talk a bit about how I proceed from here. One of the reasons for the delay in producing this video is that I've been working on issues related to, but not central to, implementing floating point circuits. For example, if I want to display binary 32 and binary 64 values in a human-readable form, this is easy. Most modern computers support 32 and 64-bit floating-point numbers, and I can use C or C++ print facilities to do the conversion to text for me. Most machines don't have similar support for binary 16 or binary 128 values. I've been working on routines to convert these values to text. I've also been working on how much performance I can wring out of the significand multiplication circuit for binary 32 numbers. And I've been exploring how best to display binary 32, binary 64, and binary 128 values given that the Basis 3 board I'm using only has a 4-digit 7-segment display. This limitation is one reason I have focused so much of these videos on the binary 16 data type. And there are other peripheral issues beginning to appear on the horizon. In a textbook, these issues would normally be placed in a sidebar. Interested readers could read the sidebar material. Those uninterested in these peripheral topics could skip the sidebars and still be able to understand the material which is the focus of the book. No doubt, some will find this sidebar material of interest. I'm pursuing these sidebar topics because they are of value to me. Since I'm doing the work anyway, I'd like to be able to share the work for those who are interested, but I don't want the sidebar material to detract from the intended focus of this channel. I could start a second playlist which has the sidebar material, or even a second channel. I'm open to hearing your opinions about which you think is the better approach, or if you think there is a third option which would be even better. In the next video, I'll take the Booth's method code developed for this video and place it into the broader context of a realistic state machine to perform floating-point multiplication. This will eventually lead back to division, I promise, but it's going to take a bit of a circuitous route. Remember that the location for the code discussed in this video can be found in the comments for this video. Please share this video with friends and colleagues who might have an interest in this series. Questions and comments are welcome in the comments section. If you found this video useful, please click like below. While you're at it, subscribe to the channel, then click the bell to be notified when new videos are available. Thanks!